All right, so this is our first set of notes. We're going to go over just the very basics behind the design of an experiment. This should be preceding our case studies that we're going to do together as a class, collaborating, whether it be online or in person. Okay, so what do we mean by experiment? I don't know that I love these examples here. Maybe we can think in real life about some and using our case studies as reflection after this. But also, I think it does touch our day to day and things like when you take a dose of ibuprofen for a headache. It was designed it was determined using an experimental design, a very special, probably what we call de-optimal design. And the procedure around that is very defined and carefully regulated by agencies such as the FDA, because experimental designs are our gold standard for understanding the effect of a single factor on a observable phenomenon. One of the key ideas of experimental design is that we're assigning treatments to units, or we could think conversely, units to treatments. We're going to be talking about this in our follow-up activity here, whether we do that activity in class or online. But there's another special attribute of any kind of experiment or experimental design, and that's just about the control of the investigator. The experimenter or investigator gets to control that assignment of treatments to units. It's not arbitrary, it's not haphazard, but it's planned and carefully regulated. That doesn't mean that it is done with complete determinism. There is a probability model used in assignment of treatments, and we'll talk all about how that should look, and we'll reflect upon that as we start looking at our first experimental designs. This is in sharp contrast to an observational study, where we may have the same kinds of observations, but the experimenter doesn't have that element of control. They don't get to decide how the units are assigned to the treatments or the treatments are assigned to the units. They simply observe what people did. Think of it this way. Let's say you're designing a drug trial. In an experimental design, you decide which research participants receive which dose of drug. In an observational study, you may just ask them, how much of the drug did you take? That is a core and important difference. Experiments are a gold standard in science because you can make causal claims. So causal claims, we've all heard the well-known saying, correlation does not imply causation. We're going to talk a little bit about that more in a bit, but that element of being able to make causal claims is very important. Observational studies find associations. Now, there are new developments in statistics such as causal modeling, which kind of bridge between those two areas. And we'll talk a little bit about that towards the end of the course, I believe. But I want us to not think too strongly at this point that there's only observational studies and only experimental studies, because there's a lot of kind of quasi experimental designs or causal studies that are kind of in between. And in the era of big data too, I'd say this line is getting a little bit even more blurred. So we'll talk about that as we get to that material in this course. But right now, just make sure you understand that key distinction between observational studies and experimental studies. So here's one of my favorite cartoons to imply. Take a moment, pause the video, go ahead and read it. If you're not getting it, then maybe you need to review the concept of correlation does not imply causation, because the end is a little bit funny. It's not laugh out loud funny perhaps, but it's a little bit poking fun at human nature and our willingness to believe causal claims from observational studies. And it's so difficult not to do that, even for well-trained statisticians. So why? Why do we bother with designed experiments? It's certainly easier just to collect observational data. Well, we have very specific designs that allow for certain kinds of treatment comparisons. So let's say you're looking at how, say, an animal might respond to a certain electrical stimulus when applied to a region of interest in the brain. This should be done in a very careful way so that you can really see the differential impact of those different stimuli on that region. Using a well-planned experimental design, point number 2 here, also reduces bias in your comparisons that you end up making for the overall means. So this will reduce your systematic errors. As scientists, it's very easy to fool yourself sometimes that you're doing good science, but maybe you've introduced a bias by not collecting or not analyzing your data in the correct way. We will talk a lot about efforts, either through random effects or blocking, to reduce variation in the response. We can improve our precision of our estimators. We can improve our ability to find true effects in the data if we're careful about reducing variability. We can make variability estimable. So we can assume multiple sources of variability in an experiment, and we can estimate it and understand those relative impacts of that variability. This may be hard to understand right now, but we will do this in earnest, especially as we talk about, again, blocking and random effects. We use design to be able to broaden our validity of the study. Without a truly done experimental design that's well carried out, the validity of your research results will be questioned. So keeping to a well-designed experiment is to your advantage as a scientist. And then finally, we can make causal claims when we use an experimental design. This again is that gold standard, that traditional experimental design that allows you to say, if A, then B. Some design goals are in opposition, so sometimes we have to make some hard decisions as we design experiments, and we'll actually have a little bit of experience with that this week in our experimental design game that we're going to play online. And we're going to continue to have to make those difficult design conditions. I would say only in the most simple cases do I not have to make some difficult decisions when I'm designing an experiment. It's usually not straightforward, and it's usually not trivial. Okay, there's a handout that I want you to pull out now. This has our terminology. We're going to be using it as we go through the case studies. I want you to spend a little bit of time. I'm not going to go through in the notes and make sure you understand all this. I think that this should be part of the activity instead. But make sure that you've, at this point, gotten that handout and that you either bring it to class or bring it to our online session where we go over our case studies in experimental design. We're going to talk about experimental units versus measurements or measurement units. If a group of units has the same treatment, then they are measurement units rather than experimental units. This is an important distinction. Let's talk about this because I think you really need to see applied settings to understand this concept. It's kind of odd out of context. We're not going to talk any more about these responses. This is actually from the textbook. Sometimes with Gary's notes, sometimes I will skip certain slides, and this is certainly one of them. Okay, so in our next part of our session, we're going to be reading through as breakout groups our experimental design case studies. And I want you to specifically pay attention to how it is or is possibly not an experimental design. thinking about its strengths and weaknesses, but then also reflecting upon these terminologies, these terms that we use quite common, making sure that we have a clear understanding, or at least a baseline understanding for these terms before we move on.